the first part of plane area by integration focus on finding the area of the region under a curve. Okay, this time we're going to find the area between two curves. And if we will consider two functions f and g, which are continuous on the closed interval from a to b, and if the function f of x is greater than or equal to the function g of x for all x within the closed interval from a to b, then the area of the region bounded above by y is equal to f of x, below by y is equal to g of x, on the left by x is equal to a, and on the right by x is equal to b is area is equal to the integral of f of x minus g of x dx. Okay, limits to be evaluated from the lower limit a to the upper limit b. And this is also equal to the integral of y sub h minus y sub l, meaning y upper minus y lower times the differential of x from the lower limit a to the upper limit b. Now, why is it that we have y upper minus y lower, or y sub h minus y sub l? Now, we can actually look at this on the rectangular plane. Okay, let this be the y-axis, and let this be the x-axis. And we are going to consider two curves, one which is representing the function y is equal to f of x, and another curve below, which is the representation of the function y is equal to g of x. And we will consider the region bounded above by f of x and bounded below by g of x within the closed interval from a to b. So let this be x is equal to a, and let this be x is equal to b. We are considering the closed interval from a to b, and f of x and g of x are continuous within the closed interval. So if we have the closed interval from a to b, then the region will be bounded on the left by x is equal to a, and on the right by x is equal to b. Hence, we're actually considering this region, this shaded region, okay, which is bounded above by y is equal to f of x, bounded below by y is equal to g of x, on the left by x is equal to a, and on the right by x is equal to b. Now, if we are interested with the area of the region bounded by the two curves, then we must represent it using the representative element. Now, of course, we know that the representative element may either be vertical or horizontal. But please take note that in this case, if we are going to consider the horizontal element, then there will be problem in the representation of the length. No, it is not consistent all throughout. Like in here, okay, in this region above the horizontal line, it is bounded by y is equal to f of x alone. Now, on the region below this line, it is bounded by y is equal to g of x alone. And on the region between these two horizontal lines, it is bounded on the left by x is equal to a and on the right by x is equal to b. So there is no consistency. Hence, if we have a region bounded by two curves, okay, above by y is equal to f of x and below by another function y is equal to g of x, it will be more convenient for us if we will use the vertical element. So if we will draw any representative element or the representative element anywhere on the region, it will always be bounded above by y is equal to f of x and below by y is equal to g of x. So let us consider this element. Okay. Now, of course, this point will have the coordinates x, okay, and let us call the y coordinate as y sub h, so that the distance of this point from the y-axis is x and the distance of this point from the x-axis is y sub h. Now, while this point, okay, coordinates are x, the x coordinate, distance of this point from the y-axis is x, and let us call the distance of this point from the x-axis as y sub l, y lower. Hence, if we will get the length of the representative element, of course, the length of the representative element is y, but since it is bounded by the two curves y is equal to f of x and y is equal to g of x, then y is equal to yh minus yl. So the length of the element is y upper minus y lower, or y sub h minus y sub l. Therefore, if we will get the area of the element is the length, which is y sub h minus y sub l, and of course, the thickness or the base is equal to the differential of x. Hence, if we are going to evaluate the integral of y sub h minus y sub l times the differential of x from the lower limit a to the upper limit b from a to b, then this will give us the area between the two curves y is equal to f of x and y is equal to g of x. Okay, that is the reason why the integral of f of x minus g of x dx from a to b is also equal to the integral of yh minus yl times the differential of x from a to b. Now, on the other hand, if the region is bounded, okay, on the left and on the right, okay, let us consider w and v be functions which are continuous, and if w, which is a function of y, is greater than or equal to v, which is also a function of y, for all values of y within the closed interval from a to b, then the area of the region bounded on the left by x is equal to v of y and on the right by x is equal to w of y, below by y is equal to c, and above by y is equal to d, then the area is equal to the integral of w of y minus d of y times the differential of y, limits going from c to d, and this is equal to the integral of x right minus x left, okay, with respect to y, limits going from c to d. Now, if we are going to look at this in the rectangular plane, okay, let us draw the y-axis and let us have this as the x-axis. This time, we will consider this curve on the right and let this be the function x is equal to w of y. And we will consider another curve here on the left, okay, and let this be x is equal to v of y. Now, we will consider the closed interval from C to D. Therefore, the region will be bounded below by y is equal to C and bounded above by y is equal to D. We're actually considering this region, and we are interested with the area of this region bounded on the right by x is equal to w of y, on the left by x is equal to v of y, below by y is equal to c, and above by y is equal to d. And if the region is bounded by two curves on the left and on the right, it will be more convenient if we are going to use a horizontal element this time. Okay, now if we will consider a horizontal element, and if we will draw it anywhere on the region, consistently, it will always be bounded on the right by x is equal to w of y, and on the left by x is equal to v of y. So if we will call this point on the curve as a point whose coordinates are x, r, y, okay, x sub r is the distance of this point from the y-axis. Of course, y is the distance of the point from the x-axis. And let us call this point as a point whose coordinates are x, l, y, meaning the distance of this point from the y-axis is xl, and the distance of the point from the x-axis is y. Therefore, the length of the representative element, which is x, is equal to x right, okay, the distance of this point from the y-axis, that is x sub r, minus the distance of this point from the y-axis, which is xl. Therefore, if we will get the area of the representative element, the area of the representative element is the length x, which is equal to xr minus xl, and the thickness is, or the base is equal to the differential of y. Therefore, the area of the element is quantity x right minus x left dy. And if we will evaluate this from the lower limit c to the upper limit d, then that gives us the area of the region. Now, we can actually illustrate this, no, using the examples. Okay, and let me see. Okay, we have this as example number 3. Of course, example numbers 1 and 2 are examples on area under the curve, and we will have 2 examples which will illustrate, okay, finding the area between 2 curves. And okay, let us have the first one. Okay, find the area of the region bounded by the line y is equal to x and the parabola y is equal to 6 minus x squared. Of course, we have the line and the parabola. And to easily draw the or sketch the region, it will be more convenient if we will get first the intersection of the 2 curves. Okay, we have the 2 curves y is equal to x, the straight line. Of course, this is a straight line whose slope is equal to 1, and it passes through the origin. And we have the parabola y is equal to 6 minus x squared. Of course, the parabola is a parabola opening downward. Okay, so before we go on with the details of these 2 curves, let us first get the intersection of the 2 curves. Okay, so to get the intersection of the 2 curves, Okay, we solve the two equations simultaneously. Okay, let us call this as equation number 1 and the equation of the parabola as equation number 2. Okay, we can solve the system by substitution. Okay, just consider the second equation, the equation of the parabola, y is equal to 6 minus x squared. And since we have a system where the first equation is y is equal to x, then by substitution, we can replace y by x from equation number 1. So x is equal to 6 minus x squared. And if we will transpose 6 minus x squared to the left side of the equation, this will give us a second degree equation, x squared plus x minus 6 is equal to 0. And to determine the values of x, we can factor the left member. Of course, the factors are x plus 3, x minus 2, and we have to equate this to 0. And equating each linear factor to 0 will give us the values of x, of the points of intersection. So when x plus 3 is equal to 0, then x is equal to negative 3. And since y is equal to x, whatever is the value of x will be the corresponding value of y also. So if x is negative 3, then y is negative 3 also. Therefore, we have a point of intersection at negative 3, negative 3. Now, on the other hand, if we will equate the other factor, x minus 2 to 0, this will give us x is equal to 2. And since y is equal to x, when x is equal to 2, then y is also equal to 2. So we have another point of intersection at 2, 2. So the point of intersections, it is rather the points of intersection of the two curves y is equal to x, a straight line, and the parabola y is equal to 6 minus x squared are negative 3, and 2, 2. Now, if we will consider the parabola y is equal to 6 minus x squared. Okay, we know that this is a parabola opening downward. Okay, and to locate the vertex for us to easily draw the region, okay, we can express this in the standard form. And we can transpose negative x squared to the left member and y to the right member so that you will have x squared is equal to negative y plus 6. Okay? So the standard form is x squared equals, we need to factor out negative 1 so that the right member is negative quantity y minus 6. We have a parabola opening downward and the vertex is at 0, positive 6. Okay, the vertex of the parabola is at 0, positive 6. The intersection of the line and the parabola at 2, 2 and negative 3, negative 3. Therefore, we can now draw the region. Okay, so let this be the y-axis, and we have the x-axis. Okay. Let us locate first the intersection of the two curves. We have 2, 2. Okay, so this point of intersection has the coordinates 2, 2, and another point of intersection at negative 3, negative 3. Okay, so minus 3 minus 3. Of course, it will be very easy for us to draw the line since 2 points determine a straight line. So we just connect the 2 points of intersection, and of course we have to show that the line y is equal to x passes through the origin. Okay, so this is the line y is equal to x. Okay, let us label the graph properly. We have y is equal to x. And the parabola y is equal to 6 minus x squared is a parabola opening downward with vertex at 0, 6. Therefore, we have to locate the vertex. Okay, we have 1, 2, 3, 4, 5, 6. Okay, approximately this is where the vertex is. Okay, vertex of the parabola opening downward is at 0, 6. So we can now draw the parabola. The parabola opening downward. Of course, it will intersect the line y is equal to x at 2, 2 and negative 3, negative 3. Okay, so this is the parabola. And let us label this. We have the parabola whose equation is y is equal to 6 minus x squared. And we are interested with this, with the area of this region, of the shaded region. Okay, now please take note that since the region is bounded by two curves above and below, okay, above by the parabola y is equal to 6 minus x squared, and below by y is equal to x, we have to use the vertical element. Okay, now note that if we will use the vertical element, anywhere we draw the vertical element within the region, it will always be bounded above by the parabola and below by the line. Okay, so let us draw the representative element. Okay, let this be the representative element. The representative element is vertical and it must touch the boundaries. Bounded above by the parabola and bounded below by the line. Okay, so we have this representative element, and of course, we will let the coordinates of the point, okay, on the parabola as x, y sub h. And this point on the line will have the coordinates x, y sub l. Okay, and if you want to get the area of the rectangular element, which is vertical, of course, the length is equal to y. But y is equal to y upper minus y lower. And the thickness, of course, is equal to the differential of x. Therefore, if we will get the area of the element is the length, okay, which is y upper minus y lower times the thickness, which is the differential of x. And if we are going to evaluate the integral within the closed interval from negative 3 to positive 2, take note that the variable of integration is x. Therefore, the interval must be from negative 3 to positive 2. X is equal to negative 3 and x is equal to positive 2. Lower limit of integration is minus 3. Upper limit of integration is positive 2. But please take note that the integrand is in terms of YH and YL. We have to express Y sub H and Y sub L in terms of the variable of integration X. And since Y upper is determined by the parabola, then we shall call this as Y sub H, okay, and this as Y sub L, since the line is the boundary below the region, or the region is bounded below by the line y is equal to x. So we can write here that y sub h is equal to 6 minus x squared, and y sub l is equal to x. Hence, going back, okay, the area is equal to the integral from negative 3 to positive 2, okay? Y sub h is 6 minus x squared minus y sub l. Y sub l is x. And we will integrate this in x. Okay, and evaluating the integral will give us, okay, integral of 6 dx is 6x minus the integral of x squared dx is x cubed over 3 minus the integral of x dx is x squared over 2. And we have to evaluate the indefinite integral from the lower limit minus 3 to the upper limit positive 2. Okay, therefore, evaluating the indefinite integral at the upper limit 2 will give us 6 times 2 minus 2 raised to the third power over 3 minus 2 raised to the second power over 2. Then minus the value of the indefinite integral at the lower limit negative 3. So minus quantity 6 times negative 3 minus negative 3 raised to the third power over 3 minus negative 3 raised to the second power over 2. And then just simplify. Okay, and we have 6 times 2 is of course 12. Okay, 2 raised to the third power is 8. Okay, so minus 8 over 3. Okay, then minus 2 raised to the second power is 4 divided by 2 will give us 2. Then minus quantity. 6 times negative 3 is negative 18. Okay, negative 3 raised to the third power is negative 27 divided by 3 will give us negative 9. Negative is positive. So plus 9 minus negative 3 square is 9. So 9 over 2. And simplifying further, 12 minus 2 is 10. So that gives us 10 minus 8 over 3. Negative 18 plus 9 is negative 9. Negative is positive, so positive 9. And minus negative 9 over 2 minus is positive. Okay, 9 over 2. Okay, giving us 10 plus 9 is 19 minus 8 over 3 plus 9 over 2. Of course, the common denominator is 6. Okay, and if we will multiply 19 by the common denominator 6, that will give us, okay, we have 54 plus 5, 114. Okay, 114 minus 6 by 3 will give us 2 times 8 is 16. Okay, then plus 6 by 2 will give us 3, and 3 times 9 rather is 27. Okay, hence the area is equal to negative 16 plus 27 is 11, and 114 plus 11 is 125. Okay, So the numerator is 125 over the denominator 6. Therefore, the area of the region is 125 square units. So we were able to find the area of the region bounded above by the parabola y is equal to 6 minus x squared and below by the line y is equal to x. Okay, remember that if the region is bounded by the two curves above and below, we use the vertical element. It will be more convenient if we will use the vertical element. Therefore, the area is equal to y upper minus y lower times the thickness, which is the differential of x, and then simply get the limits of integration. Okay, and we're talking here of the lower limit equals, the lower limit rather is x is equal to -3, and the upper limit is x is equal to +2. Now, this time let us consider the other example. And this time we will find the area of the region bounded by y is equal to 1/2 of x and y squared is equal to 8 minus x. Of course, y is equal to 1/2 of x is a straight line passing through the origin, and y squared is equal to 8 minus x. Since the second degree term is y, then this is a parabola opening to the left, since this is negative x on the right side. Okay, and if we want to get the intersection of the two curves, the straight line and the parabola, we have to solve the two equations simultaneously. And let us consider the first equation, the equation of the straight line, y is equal to 1/2 of x. Of course, we can also write this as 2y is equal to x if we will multiply both sides of the equation by 2. Let us avoid fraction. Okay, so well, anyway, the first equation is the equation of the line x is equal to 2y, and we shall call this as equation number 1. And the other equation is y squared is equal to 8 minus x, the parabola. And if we will solve the two equations simultaneously, okay, we have a system consisting of the equation x is equal to 2y and y squared is equal to 8 minus x. And we can do elimination by substitution. We can replace x in the second equation by 2y from the first equation. So considering the equation y squared is equal to 8 minus x, since x is equal to 2y from equation number 1, then this will result to y squared is equal to 8 minus x is 2y, so minus 2y. And writing this in the standard form will give us y squared plus 2y minus 8, okay, transposing 8 minus 2y to the left member of the equation, will give us y squared plus 2y minus 8 equals 0. And the left member, y squared plus 2y minus 8, is factorable. Okay, we can have the factors y plus 4 and y minus 2, okay, equated to 0. And if we will equate each linear factor rather to 0, then y plus 4 is equal to 0 and y is equal to -4. On the other hand, y minus 2 is equal to 0, so that y is equal to +2. We have two values of y and we need to get the corresponding values of x to get the intersection of the two curves. Okay, we are actually getting the intersection of the two curves. Okay, let me write it here. Okay, We want to get the intersection. Okay, so how do we get the corresponding values of x? Okay, we can actually consider the first equation. Since x is equal to 2y, if y is equal to -4, then x is equal to 2 times -4, which will give us x is equal to -8. Therefore, we have a point of intersection at -8, -4. On the other hand, if y is equal to 2, then the corresponding value of x is 2 times y, so 2 times 2, or x is equal to 4. Therefore, the other point of intersection is at 4, 2. Hence, we say that -8 rather, -4 and 4, 2 are the points of intersection. Let us just call this as POI, points of intersection. Hence, if we will draw the region bounded by the two curves, okay, we have the line x is equal to 2y, or y is equal to 1/2 of x, and we have the parabola y square is equal to 8 minus x. Okay, let us consider first the parabola, okay, and determine the vertex of the parabola. The parabola is y squared equals 8 minus x. Let us write this in the standard form. Y squared is equal to -x plus 8, so that y squared is equal to, factor out -1, so that we will have minus quantity x minus 8. We have a parabola opening to the left, okay, because of the negative sign here. Okay, it opens to the left and the vertex is at 8, 0. Okay, so let us now draw the region. Okay, let this be the, wait, I will just have it further to the right. Okay, let this be the y-axis, and let this be the x-axis. Okay, the points of intersection are at 4, 2. Okay, so we have 1, 2, 3, 4, 1, 2. Okay, this is one of the points of intersection, coordinates 4, 2. And the other point of intersection at -8, -4, -1, 2, 3, 4, 5, 6, 7, 8. -4, -1, 2, 3, 4. Okay, so approximately, this is where the other point of intersection is. And the coordinates are -8, -4. And if you want to draw the line y is equal to 1/2 of x, or 2y is equal to x, we simply connect the 2 points of intersection. Of course, we know that the line passes through the origin. So at least we have to show that the line passes through the origin, since the y-intercept is 0. Okay, so this is the line. Okay, let us label this. The equation is x is equal to 2y, or y is equal to 1/2 of x. And the parabola is a parabola opening to the left with vertex at 8, 0. This is 4, 5, 6, 7, 8. This is where the vertex is. And the parabola opens to the left, and it will intersect the line x is equal to 2y at the 2 points of intersection. Okay, so we have this parabola. Okay, let us label. This is the parabola whose equation is y squared is equal to 8 minus x. And we are interested with this shaded region. We are interested with the area of this region bounded on the right by y squared is equal to 8 minus x and on the left by x is equal to 2y. Now, since the region is bounded on the left and on the right by the two curves, then it will be more convenient for us if we will use the horizontal element. Okay, and please take note that if we will use the horizontal element, okay, it will be consistently bounded on the right by the parabola and on the left by the straight line. So if we will draw the representative element, horizontal representative element anywhere on the region, okay, it must be parallel to the x-axis and must touch the boundaries, the parabola and the straight line. Okay, so this is the representative element, and we represent this point by the coordinates x, right, y. Okay, the distance of this point from the y-axis is x, right. Okay, and the distance of the other point, okay, the point on the straight line will have the coordinates x, l, y. The distance of this point from the y-axis is xl. Of course, if you will get the area of the element, it is equal to the length times the thickness. The thickness, of course, is the differential of y. And the length is equal to x. But x is equal to x right, okay? X is equal to x right minus x left. Okay, x right is determined by the parabola and x left is determined by the straight line. Okay, now what is XL? Of course, XL is based on the equation of the straight line. So the straight line is x is equal to 2y, therefore XL is equal to 2y. On the other hand, if we have the equation of the parabola, y squared is equal to 8 minus x. Okay, if we will solve for x, then if we will solve for x is equal to 8 minus y squared. And since the parabola is the boundary of the region on the right, then we say that XL, or rather x right, is equal to 8 minus y squared from the equation of the parabola. Okay, and if we are going to write the equation of the area of the element is equal to the length, which is x right minus xl times the thickness, which is the differential of y. If we are going to evaluate this from the lower limit, okay, look at the points of intersection, -8, -4, and 4, 2. So the lower limit of integration is y is equal to -4. Take note that the variable of integration is y. So we have to determine the limit of integration as the values of y on the points of intersection. So y is equal to -4, okay, lower limit of integration, and the upper limit of integration is y is equal to 2. Okay, but since the integrand are xr and xl, we have to express this in terms of y. Okay, hence we have the area is equal to the integral from -4 to +2 of xr. Xr is 8 minus y squared minus xl. Xl is 2y, and the thickness is the differential of y. Hence, we can now evaluate the integral. The integral of 8 dy is 8y minus the integral of y squared dy is y cubed over 3 minus integral of 2y dy. Of course, the integral of 2y dy is 2y squared over 2, and 2 will cancel. Hence, this will give us y squared. And this must be evaluated from y is equal to -4 to y is equal to 2. Hence, the area is equal to the value of the indefinite integral at the upper limit 2. So 8 times 2 minus 2 raised to the third power over 3 minus 2 raised to the second power minus the value of the indefinite integral at the lower limit, -4. So 8 times -4 minus -4 raised to the third power over 3. Okay, then minus -4 raised to the second power and close. Then just simplify the result, no? Okay, and what is 8 times 2? Of course, 8 times 2 is 16. Okay, so we have 16 minus 8 over 3. 2 square, of course, is 4. Okay, then minus quantity. 8 times -4 is -32. Okay, -4 raised to the third power is -64, minus minus is positive. Positive 64 over 3. -4 square is 16, so minus 16. Okay, hence we have 16 minus 4 is 12 minus 8 over 3. Okay, -32, -16 is -48, minus minus will give us positive 48. Minus 64 over 3. Now 12 plus 48, of course, is 60. -8 plus -64 over 3 is 72. -72 over 3. So we will have 60 minus 72 is divisible by 3, right? We will have 24. Okay. 72 by 3 is 24. And 60 minus 24, of course, is 36. Therefore, the area of the region bounded on the right by the parabola y squared is equal to 8 minus x, and on the left by y is equal to 1/2 of x, or x is equal to 2y, is 36 square units. So we were able to solve 2 examples, no, which illustrates how to get the area of the region bounded by 2 curves. Okay, now please take note that when the region is bounded by 2 curves above and below, we have to use the vertical element. It will be more convenient to use the vertical element, just like in example number 3. And if the region is bounded on the left and on the right by the 2 curves, then it will be more convenient if we will use the horizontal element. Okay, and you will notice that consistently, just like in this example, in example number 4, the region is bounded on the right by the parabola, and on the left by the straight line. So if we will draw any horizontal element within the region, it will be always bounded on the right by the parabola and on the left by the straight line. Okay. Now, in our uh, future lesson, no, like in finding the area of the centroid, we will have more examples on how to find the area. Okay, so additional examples in finding the area will be considered when we discuss centroid of plane area. Okay, so in finding the centroid of plane area, we will start from scratch. Okay, sketch the region. Okay, draw the element. Okay, find the area before we find the centroid of the area. Okay, so this finishes part 2 of plane area by integration.